Okay, this is to clean up the rest of 1.5. It's not that much because we already kind of went through the example. So, oopsie. Got 1.5. So I'll call it 1.5b, and this will be covering now solutions of non-homogeneous systems. So in lecture, the in-person class part, we talked about the homogeneous systems quite extensively. We talked a lot about what to do when you have a matrix equation that is set equal to the zero vector. So we've already really hashed this out, and so now the question is going to transition to what to do if we have just a not zero vector. So B doesn't necessarily have to be zero. So homogeneous, non-homogeneous. And as hinted at in the last example that we kind of rushed through in class, there is a pretty close relationship between the solution sets of these two types of equations. So we'll be talking about that some. The first thing here, this kind of summarizes it so we know what to be looking for. When a non-homogeneous linear system has many solutions, the general solution can be written in parametric vector form as one vector plus an arbitrary linear combination of vectors that satisfy the corresponding, and here's our relationship to the homogeneous stuff, corresponding homogeneous system. Okay, so that's a lot of words again. When there's a lot of words, typically there is a more elegant way to understand this. So for now, let's read through this, and then we'll actually return to this slide later on. So when a non-homogeneous, so this means that I've taken a matrix equation, it's not necessarily set equal to zero, the vector. We take that linear system, and if it has many solutions, in other words, it has infinitely many. The only way you can have many solutions is for there to be infinitely many solutions. Then that means your general solution, we can express what the solution is by taking some vector and then adding an arbitrary linear combination of some other vectors. And those other vectors essentially are the ones that satisfy the corresponding homogeneous system. What does that mean? Say I took my non-homogeneous equation and then replaced it with a zero vector to make it homogeneous. So then we're saying that these vectors that we're taking the linear combination of, they are solutions to this equation. And so the difference between the solution sets is then stuff that satisfies this one, and then shifted by some or added to some vector, some other vector, to adjust for that b. Okay, so let's go to the example we did in class and kind of think about that in the back of our minds. So if we want to describe all solutions of a non-homogeneous equation because it's ax equals b and not 0. So let's define our matrix A. We'll have, and I'm going to use the same one. This should look like a familiar matrix, and that's intentional because I want there to be some level of comparison between the homogeneous version and the non-homogeneous version. So we'll take our 3 minus 3, 6. So if you're taking notes, find your page where we covered this problem and be able to reference it when we do the conclusions for this problem, because that is kind of inherently the whole point of learning this part of the text. And so our b is going to be 7 minus 1 minus 4. And so if I took 3 minus 3, 6, 5 minus 2, 1, minus 4, 4 minus 8, and then make an augmented matrix with our b vector, 7 minus 1 minus 4. What we did was we showed that this is row equivalent to 1, 0, 0, 0, 1, 0, minus 4 thirds, 0, 0, minus 1, 2, 0. Now, if you had gone back to your, like I said, go back to your notes to when we did the homogeneous version of this, this section right here should look precisely the same as it did. The only thing that's different between the homogeneous version and this is the fact that that's not just going to be 0, 0, 0. That's actually have some values. And I'm shortcutting the computation process because you already know how to do that. What does this tell us? Well, this tells us that x1 minus 4 thirds x3 is equal to negative 1. Tells me that x2 is equal to 2. And then, as we can see, the whole bottom row of zeros is going to mean that x3 is free. And if I want to represent this solution now parametrically, so that's going to imply a parametric solution description. X1 is equal to negative 1 plus 4 thirds x3, x2 is equal to 2, and x3 is allowed to range, so x3 is free. Then that's going to tell me that I can now write my solution set, the vector x, solutions x, as, well, how many components do I have? I got 3 components, x1, x2, and x3. So, again, we did this in class, same routine. What's x1? I'm going to plug it in. Minus 1 plus 4 thirds x3. What's x2? Well, x2 is 2, the constant 2. And x3 is itself. And whenever you have a free variable, you just plug it in, standing in for itself. And then again, we want to separate out the different, sort out the terms. So all constants by themselves and all x3s by themselves. So I've got the constant term on the top is minus 1. Constant term here is 2. Now, is there a constant? No, so it's 0. So I put 0 plus, and then now I have whatever's left, right? So 4 thirds x3, no x3s, so that's 0, and then I have an x3 here. So if I factor out, so here's my constant vector, and if I factor out the x3, the free variable, then I get 4 thirds, 0, 1. Now what you'll notice is that this right here is the solution to the homogeneous version of the equation. Linear combinations of this here vector. What's the difference? Well, we've taken some sort of shift. We've taken and added another vector. And so what I'm going to do is I'm going to cut between these sides. So when a non-homogeneous linear system has many solutions, so let's see if that's the case. We in fact have that a non-homogeneous system has many solutions. Okay, fantastic. That's the first thing. So that means what follows counts. The general solution can be written in parametric vector form as one vector plus an arbitrary linear combination of vectors that satisfy the corresponding homogeneous system. So if I'm going to color code this so we can keep track of everything, the general solution can be written in parametric vector form as one vector plus an arbitrary linear combination of vectors that satisfy the corresponding homogeneous system. Okay, so we're going to look for these components. What is the general solution? Well, the general solution is just the entire thing, right? This is the general solution of the non-homogeneous system of equations. So that's our red. And then what is the one vector? Okay, so the one vector is that constant vector that we found. So this right here is our one vector. And then plus, it said an arbitrary linear combination of vectors, in this case, that satisfy the corresponding homogeneous system. Okay, so again, go to your notes. We did the exercise, we worked through it, we worked through the homogeneous version of this problem. And when you work through the homogeneous version of the problem, the solution gives you this vector, all linear combinations of this vector. So this satisfies the homogeneous system. So what we have here is in red is our general solution to the non-homogeneous version of the equation ax equals b. In blue, we have our sum vector, right? Sum vector that's added then to the arbitrary linear combinations of, so linear combinations of the vector that satisfies the homogeneous, that satisfies the corresponding homogeneous. So earlier we solved this problem equivalently for this. And when we did that, we got this solution, the 4301, and then all linear combinations of that. Now we turn it to this non-homogeneous version, and then we get that same exact solution, and the only difference is now we have added some vector to it, right? Some shift. And so that means that these solution sets are going to be parallel. Now, they're parallel lines in this case. So that's a little bit more expansion on that example that we kind of had to rush through. So then there's just two more quick things here to talk about. Let's see. This is really just a summarizing theorem of the observations we've made. So suppose, that's a terrible, okay. Suppose the equation ax equals b is consistent, so that just means it has at least one solution, is consistent for some b, and we're going to let p, some vector p, be a solution. Okay, so our system is consistent, which means that there has to exist a solution. We'll call one of those P, for example. Then the solution set, of ax equals b, the non-homogeneous equation here, is the set of all vectors of the form W is P plus V sub H, where V sub H that vector, is any solution of the homogeneous equation, ax equals 0. And again, this is just restating all of this stuff over and over and over again. What would be considered our p here? Well, the blue is our p. So this right here is the p, as same analogously. And then this purple bit, the solution to the homogeneous system as we found, and that all put together is going to generate our general set. So all of those. Okay. So, last thing here is just the baseline algorithm for writing a solution set of a consistent system. So, whoops. So writing a solution set of a consistent system. So we don't want not inconsistent. So of a consistent system in parametric vector form. You're going to need to know how to do this. 1, you need to row reduce the augmented matrix. To reduced echelon form. Second, we want to express each basic variable, in terms of any free variables, if we have them. In terms of any free variables. Obviously, if you have no free variables, then just don't worry about it. 3, we then want to write a typical solution X, as a vector, whose entries depend on the free variables. If any, so there might not be. And then lastly, we want to decompose our vector x into a linear combination of vectors with numeric entries. Using the free variables as parameters. Okay, so this is a lot of words again. All this is a summary in words of what we've been doing in class with the examples, with all of the examples. So like, for example, step 1 is row reduce the augmented matrix. Okay, so when we went back here, that was in fact our step 1. So we identified the matrix equation, we made it augmented, there's our augmented matrix, and so this, from here to here, was step 1. And we learned how to do that in section 1.1. Okay. Step 2, express each basic variable in terms of any free variables. Okay, so where do we do that? We are expressing our basic variables in terms of any free variable. So we kind of strip the information here, and then here's our free variable, so now we're expressing it. So this is step 2, right here. We express our basic variables in terms of that free variable in the example. Okay, that's step 2. 3, we want to write a typical solution x as a vector whose entries depend on the free variables, if there are any. We do have one, so we'll expect that. So write it as a vector x. And so what do? Well, I say here's my vector x in terms of its entries, in terms of the free variable. So now it's written in terms of the free variable. This, from there to there, is step 3. Okay? And then step 4, of course, is then decomposing that x into a linear combination of vectors. We need the vectors to be numeric entries without variables in them. And then the free variable pops out as a parameter. We factor it out. So that step, going from this to pulling out this and then factoring this out in a linear combination, that final step 4. So you know what all of these things are. This is just summarizing what you already know how to do mechanically in words. Okay, so that is all. It's nice and short. Clean up the rest of 1.5. And then we'll start talking about linear independence in the next lecture.